All right, so welcome everyone. This is the last instruction day for staff. It's kind of a sad day. Sorry, I'm seeing there we go. So let's look at the schedule just so we're all on the same page as to what's about to happen in the coming week, really. So here we are, November 18th. We've actually covered quite a bit of this. We're going to be talking about regression and correlation this last bit here. So that's the goal for today. Next week, there is no class because it's Thanksgiving. So I hope all of you get to safely spend time with family and stuff your faces with whatever favorite foods you have for Thanksgiving. And then we will return on the 2nd, December 2nd, and that is our final exam, final project piece. So both come together. So the reason why both are listed is that there's going to be an exam that's going to be like your other exams in this class, more traditional exam. And then the project will be a separate document in Course Connect that you'll need to access and run some analysis. So the exam is going to be like in the past where you write in right after the question, what is your response? And you may need to graph if you want to on a separate piece of paper like you guys have done before, totally fine. But the final project will be a data set and you will need to run some analyses in Excel and then submit your results.
So the final project is not something we are able to work on? It's an exam?
It's going to be in the class, yes, in this December 2nd piece.
So it's part of our exam?
Yes.
Oh, I didn't know that. Uh-oh.
Does that make
sense?
What's wrong?
I thought we would have time to work on the final project at home.
We can do it that way. There's really no need. The way I've done it in the past is that it was done all in the same class session. So what I plan on doing is you guys will have both of this. You'll have the exam and the data set for the final project. It'll go live that Wednesday and it'll be due by Friday, both pieces.
Okay.
But they will both, what's that?
Okay. I just said okay.
Okay, sorry, it kept breaking up. I could just hear So, yeah. So the idea is that you don't need to do a whole write-up. There's no research ahead of time. It's not a project that you're going and working on it at home on like gathering resources or literature. That's not the goal of it. It is going to be a data analysis that you'll need to run and then submit the results.
Okay, I thought that it was going to be like last time where we had class time to do like in the first exam, we had a class period to have our exam type of thing.
Okay, I'm understanding now your question. I was not understanding that earlier when you were like, is it like an exam? I was like, sure, yeah, it could be an exam. I see what you mean now. You are not going to be limited to the 3-hour window of our class for that, no. Does that answer your question, Elizabeth?
Yes, yeah, thank you.
Okay, I just want to make sure that no one thinks they need to do additional work ahead of time. Like the word project implies that like, wow, you've got a lot of other stuff to do. It isn't. It is almost like a separate part of the exam like we've had before, but because it's a lot meatier, you get extra time. Does that help?
Yeah, thank you.
Okay. Any other questions about what is to come, the exam and final project? Okay, my hope is to still introduce the exam during our class period on Wednesday the 2nd. It's just a good meeting place to be like, hey, if you have any questions, anything that you see that I can be helpful with, you do not need to attend. All of you have my cell phone number as well. You can feel free to call or text me if you have questions, so I can be helpful that way. Sound good?
Sounds good.
Okay. All right. So let's dive into what we are doing today. Whoops. Okay, so we're going to be talking about regression and correlation today. Some of the goals for today will be to be able to describe the linear relationship and be able to see the predictive rules of bivariate and multiple regression models. We'll talk about that in just a second, because yeah, this is not like a forecasting, future telling. It doesn't do that, but it does provide an idea on trends of the relationship. So there are some predictive value within that. We'll talk about the best fitting line. That's going to be huge, and how to interpret and calculate the following values for a regression line. So you'll need to know about a beta, and quite simple actually. You'll need to also know how to interpret a Pearson correlation coefficient. And obviously you don't need to worry about the SPSS output. That's not something that we're going to look at obviously in this class, because we don't have access to SPSS. Okay, so first off, scatter diagram or scatter plot. That is something you've likely seen multiple times. It often looks like this. We have several coming up for today's class, but something like this, where you've got a bunch of, I can't see your faces now, so I don't know if you can see what I'm showing you. You've got an axis and then several points along the line. So it shows the intersect between this Y variable and this X variable, and you see where it connects. That is a scatter plot. What it does is it's a visual representation to describe the relationship between two, specifically interval ratio items. It is not a nominal descriptor, it is for interval ratio. Oftentimes we use it to explore what is the relationship before we go into a regression analysis, because then it gives us some idea as to how they're associated with one another. So that's a scatter plot. A correlation is a measure that's associated, a measure of association, I should say, that's used to determine the existence and strength of a relationship between variables. And it's quite similar to a proportional reduction of error, which we briefly went over in chapter 10 last week when we talked about ANOVAs. Correlations are either positive, negative, or no correlation, or zero correlation. We'll dive into a little bit more definition of that in just a minute. A regression, which in statistical terms can also be referred to as a prediction, is a linear prediction model using one or more independent variables to predict the value of a dependent variable. So that's the overarching idea behind a regression. Then it splits off into a bivariate regression or a multiple regression. In a bivariate regression, it examines the effect of one independent variable to a dependent variable. So again, bivariate, just two variables. With multiple regression models, it examines the effect of several independent variables on the values of one dependent variable. So let's give an example of that real quick. I think we've talked about this example before, but the idea of college success. What is predictive of college success? Hold on just one second. I've got a puppy who likes to chew on a bone, and then he gets confused and starts pulling the carpeting, which is no bueno. So we talked about college success, right? Colleges are interested in knowing what's going to lead to a successful college student within our institution. They're going to come up with a variety of independent variables that will act as predictors of success. Now, maybe that one is stronger than the other, but we can look at all of those independent variables in a multiple regression to figure out which one is most predictive. In other words, which one holds the largest amount of variance of the dependent variable. So we've used this example before, so hopefully there's some examples that come quickly. What might be some predictors of college success? Like if you're a high school student and an admission counselor is debating, should we, shouldn't we, what are some factors they should look at?
SAT scores.
SAT scores, good. What might be something else? Oh, Elizabeth, you had the same idea, SAT scores.
Or are we talking academic success or overall success?
Oh, I love it, Elizabeth. Please take research methods with me, right? So that's a very good point. Yeah, how are we going to measure success? We probably need to define that, right? So yeah, let's say academic success is what we mean. So yeah, Eliza came up and said GPA, very good. Other examples come up?
After school programs. So if you're
okay, so
student council or whatever.
Totally. So after school programs, or maybe even extracurricular activity or school involvement, or yeah, those would all be good.
Ooh, letters of recommendation.
Very good. So past verbal indicators of success, right? What about some interesting static variables like income? Could that play a role?
With admissions, it could.
For what?
With admissions, I guess it could.
Oh, let's walk right into that little crisis that we had here in Michigan a few years back. Yeah. Right. But I mean, even just looking at parental or family income, oftentimes can be a predictor, because how many resources is that student going to have to help them succeed? May not be one that we like talking about. Yeah, for books, exactly. Oh, and Greg, don't worry, we didn't do attendance today. There was a quiz though, so if you weren't here at the beginning, remember to take the quiz. So can you see how we've come up with a ton of independent variables, right? And then if we plug them into a regression analysis, which we would do in SPSS, we would then see what are all those factors for all of our participants. What does that look like in predicting this dependent variable? And the dependent variable may be GPA in college after the first semester, right? It could be retention rates for that college, right? There's multiple measures we can look at. Or it could be a satisfaction survey score, right? How happy are they? How well adjusted are they? That could be considered success. And then we would want to see which one of our independent variables was most predictive of that dependent variable. And at the same time, we'd also want to see, are there some on there that actually have zero impact on our dependent variable or have an inverse impact? So in fact, if they're really high on this value, they're going to be much lower on this value, right? So that's the power of multiple regressions, is that you can include multiple independent variables to get a better understanding of your dependent variable. So as we've layered this class week by week, we've gotten more sophisticated in our analysis. Like even last week with an ANOVA, you can just say, right, are they the same or are they not? That's kind of the limitation. Already we're a step more refined here, more sophisticated in the analysis, because we can say which of those has an impact and which of those is the greatest of the impact. Okay. So scatter plot, this is what a scatter plot would look like. This is the relationship between the perceived stress that one experiences and road rage. This is their scores on a driving angry scale, and this is their score on a perceived stress scale. So looking at this scatter plot, what might you hypothesize about the relationship of these two variables?
They have a weak positive, is it correlation or, yeah, it's correlation. A weak positive correlation.
Okay, so let's break that down. First, why is it positive?
Because all the majority of them are all in the same direction of up.
Exactly. So if you were to create a line, it would be considered a line of best fit, right? It would be the average, so that every single point, well, yes, I see we're looking, mirror, or it's not a mirror. Okay, moving right along. Yes, this is positive to me. A line of best fit is that every dot, for the most part, is equidistant to the line, right? So you find a way so that the line is perfectly in the middle of it. Now, we call it positive because you said it goes up. Is that what you said?
Yeah. Well,
Okay.
no, it's because they're both going in the same direction.
That's it. Okay, because as one variable goes up, the other variable goes up as well. You guys can see my cursor here on the screen?
Yep.
Okay, so the further out we go, the higher the dots tend to be. If I'm over here, the dots are lower. If I'm way at the end here, the dots are a lot higher on average, right? As a whole, that is the trend that is happening. Because as one goes up, the other goes up, that is considered a positive relationship. Another way to look at it is way back when you guys did geometry and you figured out how to plot a line, right? And you figured out the slope. This would be a positive slope because it goes, right? As one variable goes up, the other one goes up. Okay, now you also said it is a mild positive correlation. Say more about mild.
It's because they're not showing a strong correlation of going in the same path. They're kind of just showing the same direction. So the dots aren't like tightly packed or together. It's not really a pattern or like, oh, it's just kind of a general trend.
Okay, very good.
Right.
So going back to geometry, do you guys remember using a protractor and you figured out the angle, right? The angle of a line. So we see that this line is a little bit more flat. It's not a perfect 45-degree or even greater, right? It's a little lower. So if you think about a zero relationship, it would be a completely flat line, meaning there is no reasoning one way or the other, right? Like it's not like as one goes up, the other goes down. It's just really completely haphazard. There is no relationship. So if you now have a positive correlation, but it's really close to a flat line, that is going to be a more mild positive correlation. Conversely, it could be the same thing. If it's like a negative correlation, but it's almost flat, same thing, more mild. Now we'll talk about numbers today and see how we can interpret that with just a value. Okay, so scatter plot, again, this is a bit of a description of it. We put the independent variable on the x-axis and the dependent variable goes on the y-axis, and then each dot represents one case or one participant in your study. So if I know, this is based on this example, the scatter diagram of educational attainment and internet hours per week. So this is saying, if I know your education in years, I can predict your internet usage. Now, where do we get this idea that we can predict? What do you guys think about that?
Would that be based on previous averages of before, where we can, based on those numbers, we can predict future wise?
So are you talking about an individual? Like if I know your previous number of TV hours watched, I can predict what it'll be in the future?
Yes.
Okay, totally true. I'm going to put a puppy outside, but I'll keep talking. In therapy, back in the day when I was doing a lot of private practice work, one of the biggest statements we always said was the best predictor of future behavior is past behavior, right? If somebody's done something in the past, they are more likely to do it again. What this means, though, with statistics is it's not looking at just one individual. It is taking what a study has come up with and it's created a scatter plot so that I can generalize it to a larger population at large. So again, if I'm using inference or statistics, I'm taking a sample to make sense of a population. So I'm not looking at the individual level. But by this, I am figuring out this is the line of best fit or the slope, or in this case for regression, it's called the beta. I know that value. So if I plug in, much like if you're trying to figure out, you know, back when you did the, way back in the day, I don't know, what is that, 7th, 9th grade maybe? geometry where you're figuring out how to create a line, how to plot a line and create the slope. If you're given the y and you know the slope, you can figure out the x, right? You can solve for it. This is the same thing. This is saying, if you give me the number of education that you have, because I know the trend that it follows, I can estimate or predict the number of TV hours watched.
Okay.
Does that make sense?
Yes.
So if somebody has a high school level education, what might we predict is the number of hours of internet, is that what it is? Internet hours that they engage in per week?
That the number of hours that they will be on the internet increases throughout their educational years?
Yep, so that's the takeaway message of the scatter plot. The more educated you are, the longer you spend on the internet every week. So then my question is, how many hours per week do you think you'd be on the internet with a high school education?
It'd be like
Or
6
12
or 7.
years.
6 or 7.
Be 6 or 7.
Is it more like 1 to 2? Because high school is 12th grade. That's senior year.
Oh yeah, never mind.
Yeah, so I'm thinking if you look between 10 and 15 years, right, like that should be 12 and a half. I would say that's like close to 4, like
4?
3.5 to 4 is what my estimate would be without my ruler checking out my screen. Does that make sense how I did that?
Yeah.
Okay. Eliza, help me understand how you got 6 or 7.
I was thinking of like the ages on the bottom, not like.
Oh, you were thinking like, okay, right. Yep. Yeah. So does that kind of make sense though, that it would be the more educated you are, the more time you spend on the internet?
It makes sense because you have to do so much more research and you're constantly double checking things.
My only thing is, so this is like my research brain can't turn off. I'm like, when was this taken? Because do you guys all get this on your phone, the amount of like screen time that you've had per week? Like this week, you averaged 3 hours more than last week. Now, granted, it's all screen time, calls, text, but is Facebook the internet?
Yes.
Yeah. So when I look at a 10th grader having less than one hour per week of internet, I call a little bit of suspicion on that because.
Okay, question. Going off yours, does texting count as internet? Because, like.
That's data. Well, I mean, unless you're using an inferior non-Apple phone. Just kidding. But yeah, I mean, that's a good question. Yeah. So I poke holes in this, but big picture, stepping away from the research question is understanding the scatter plot, regardless of what it's showing. But yeah, not a perfect example here. All right, so linear relationships. That is the relationship between two interval ratio variables where the observation displayed in a scatter diagram can be approximated with a straight line. We've just finished talking about that you can kind of draw a line through it. If it is a almost perfect linear relationship, you're going to be able to see the observations of both variables almost along this line. Now, in real life, that does not happen. Nothing is that perfectly aligned. What it tends to be is that it's like the line of best fit across all of the data points. That's a better fit. So a bit about then regression. It's a mathematical technique that is used to predict a dependent variable, and it's based on fitting the math model to actual data. So it's taking part of that model and math and then fitting it to actual data. So some of the assumptions, dependent and independent variables are all interval ratio measurements. We talked about that a minute ago. Let's see. The variables need to have a linear relationship. It needs to be in part linear. Now, you can create a variable that will, they call it a dummy variable, but what it is, it's the variable that's a yes, no. So it's dichotomous, there's only 2 options, and it's coded as 1 or 0. Oftentimes, that's what we use if we have nominal data. So for instance, such as sex, race, religion, or political affiliation, you would write sex 0 or 1, male to female. You'd have a code book that would tell you what it is. And then the same thing for race. It could be white 0, 1, yes, no. Black 0, 1, yes, no. Christian 0, 1, Catholic 0, 1, that kind of thing. So you can do that in order to have it fit the line of best fit. This is another regression technique for a non-linear model, because obviously it's not a perfectly linear, it's a curvilinear model in this instance. And it's the amount of hours of reading and age. So as you can see, when you're quite young, you're not doing a whole lot of reading. As you get older, you do a lot more. And then again, as you age, perhaps reading becomes more difficult, so it drops down again. Another one that I've seen that's actually the reverse is number of doctor's visit related to age. So when a child is first born, lots of frequent doctor's visit. As you age, you tend to have far fewer, and as you age again into older age, you start having a lot more. So that would be a U shape, but still is a curvilinear relationship. So just to be clear, there is still predictive value in here, right? Like if I know your age, I can kind of estimate how many hours of reading or doctor's visit that you have. It's just not quite as prescriptive or predictive as using the line of best fit with your beta or your slope.
Now, quick question. Is there like,
Yeah.
Is there a reason why a company or a business would want to know this, like this trend or this regression technique? Because it doesn't really, it seems like it's more of like an observational, like, oh, like we know it, but it doesn't really seem like, oh, like let's implement this plan to like profit off it. Or I'm just trying to think of like examples.
Well, so with this particular example, if I'm noticing this major drop off for people age 60 to 75 and I'm a publisher, this might impact it, right? And perhaps I start creating some hypotheses as to why the older generations are not reading. And perhaps I come to the conclusion through interviews, right, that it's because the font is too small, or, you know, it's just too challenging. Okay. So then maybe I do greater marketing for audiobooks for that group so they can still be reading, right? Or my other example with doctor's visit, actuaries use that quite often for insurance tables. So if you know, right, life insurance wise, or even health insurance, that insuring a newborn and insuring an older individual, that's going to cost you a lot more money because they just interact with the healthcare system so much more. So there's some value there.
Oh, thank you.
No problem. Okay, so finding the best fitting line. So the relationship, again, between years of education and internet hours is not perfectly linear, as we saw. It kind of jumps up and then goes off. Most relationships in the social science are not deterministic, meaning they're not perfectly linear. And so we're not able to come up with a linear equation that allows us to predict perfectly y from x. We're much more likely to find relationships approximating linearity, meaning we use words like estimate and we predict and we suspect it is like blah, blah, blah. That's the language we use. The relationship between educational attainment and internet hours can also be described with the following equation, which is equation for a straight line. This should be similar to you guys, right? Familiar at least. Y equals A plus B times X. That is the same idea as it is for a regression. We do the same thing. So within that, Y is the predicted score on the dependent variable. X is the score of the independent variable. A is the y-intercept, right? At what point does it actually cross the axis? And B is the slope of the regression line. So the change in Y with the unit change in X. So going back to that line of best fit, if I were to draw a line that perfectly captured, as close as possible, captured all of the data points, this is what I would do. So again, for somebody, this was years of education 12, you can see my estimate was even off a little bit from that. This is where I would land. So now, if I'm curious about somebody whose educational level is at age 21, I would actually just plop it into our calculation. So we would get this equation again of A plus B times X, and that's how we would calculate it and be able to then move forward with future predictions. Okay. Again, the goal of putting a line of best fit is to get the closest to our approximation, but we recognize because it's not perfectly linear, there is going to be some amount of error in our line of best fit. So that's referred to usually as residual, right? There's just a certain amount of error. So the difference between the observed Y and the predicted Y, you have it here as the error term, is again, your observed Y minus the predicted Y. So for this one, the residual ends up being negative 0.34 hours. Now the goal is to identify a line or a predictive equation that minimizes or makes it as little as possible error as we can, because we want to try to approximate it as best as we are able. The least squares line, that's the best fitting line, is a line where the residual sum of square is at the complete bare minimum. So if you do a least square method, it's a technique that really brings the line, as I was mentioning, so that there's the least amount of change between all data points. So that as, obviously, it's not going to hit all the data points, but that the difference between each is as minimized as possible. Okay, I'm going to let the puppy in again because he's barking like crazy. Any questions so far about this material? Is that making sense?
My biggest, so the least squares line and the line of best fit, what is it, in which is there, so they're different entities. So when do you choose one versus the other?
One or the other?
Yeah.
They're not. They're the same idea.
Oh,
so the finding the best fitting line. Yeah. So when you're attempting, okay.
Thank you. Sorry, I was just getting a little caught up, but yeah.
No, same thing. Yeah, you're trying to again minimize as much residual error as possible when you're doing that. Yeah.
All right, awesome.
Okay, so how do we go about computing A and B, right? Now, this is going to be a lot of data, a lot of information and formulas. You are not going to be asked to go through this. Again, this is beyond the scope of this class. You need to just have some broad awareness as to what it is. So, and what's going on with my chair? I can't scoot in. All right. So when we're computing all of this, let's take a peek here at some of the information. Some of it will be looking at the actual standard deviation of the value because you're looking at variance. Again, that's our goal. We're seeing how much of the variance is accounted for by our independent variable towards your dependent variable. So you need to know both variance and covariance. And then your line of best fit is determined here. So again, this is the mean of all y, the mean of x, A is the y-intercept, and B is the slope of the line. Okay. Look a little bit more at additional information here. So covariance, what does it mean for things to covary? That's when you're looking at the mean of each, the mean of your y, the mean of your x, and you're looking at, for instance, you're looking for 4 points above the mean of x and above the mean of y, and their contribution to the covariance will be positive because you're adding up all of the positive value. Below the mean is also going to be playing a role. So you see all these dots that fall then below the mean. So it's how the two covary together. So it's not just the variance that they share with one another, it's how much they move in the same direction. Okay. Covariance is kind of another beast. No, it exists. This isn't, I mean, again, if we're flipping it on its head, you see the dots just swapped corners. That is how we would look at the covariance for a negative slope, okay? So how do we go about finding predicted values when we're using a regression model? The same thing, this is the same idea, the education and internet hours study that we looked at earlier. So you would plug in the years of education into the model and then ask yourself if it is actually accurate. So your beta ends up being your standard deviation between variables x and y divided by your variance squared, right? So not standard deviation, but now your variance of x, which gives you a beta of 0.62. Again, gang, you guys are not going to be asked to calculate a beta. That's not the goal of this class. The goal of the class is to understand if you have a beta of 0.62, can you give me an idea as to what is the direction of your slope? That is far more what I need you guys to know. So going back to the equation of a line, right, we can plug in different values here. So for A, I have the mean of my y, right, minus my beta, which is right here, times the mean of my x. So that would be 4.5 as my mean for y, number of hours of internet, right, times my b, and then the mean of x, which is my mean education, is 14.8 years. That gives me negative 0.468. That is my A. So this then becomes the equation of my line. So as I plug in an x-intercept, I can then predict where they'll be along the line. Questions about that so far? Is that kind of making sense?
Yeah, in terms of retrieving the information for that equation right there, did that come from the previous example we were looking at?
The years of education and
Yeah.
internet hours watched? Yep. Yeah.
Okay.
Mm-hmm.
Thank you.
So
Yeah. Yeah. So when you guys go back, then look through the slides, you'll see exactly where that came from. Yeah, go ahead, Kyle.
So the x or the SXY, the 14.22.
Mm-hmm.
What is that like? What is SXY stand for?
The standard deviation of your x value times y.
Oh, I'm happy I asked. Okay, cool.
Yep.
Okay.
And then your s squared, that's variance. So standard deviation, remember, that always gets square rooted. Variance does not. So that's why it's s squared of just x.
All right, perfect.
Okay. I'm moving through this because I don't want you guys to get bogged down with all the numbers and then like freak out of you're not sure how you'll do it. Because again, this is meant to be big picture. Big picture, what does a regression mean? It means I'm looking at independent variables and their ability to predict a dependent variable. And how do I do that? It's because I have plotted and I have some data already that shows me the relationship between these variables. And then I can create a line of best fit based on those, because I can approximate them. And then I can figure out or predict or estimate if I have one value, what is my other value going to look like? Because I can plug it along the line. That is the main goal. Okay? So the B coefficient is equal to 0.62 as per our last example, which tells us that with each additional year of education, internet hours per week is predicted to increase by 0.62 hours. Boom. That is the take-home message of that number, right? So as you go up 1 year of education, that's how much more you'll go up by internet hours, okay? So again, it is a positive relationship. It is not a one-to-one, right? It's less than that, but it is still a positive relationship. Okay. Now some caveats. We never expect that our regression equation is going to make a perfect prediction for every individual case. That's not going to happen, right? It's an approximation. This is inferential statistics. We are trying to, based on past data, to get the best idea on future data and be able to estimate, but it's not going to be perfect. The y-intercept A is the predicted value of y when x is 0, okay? So it's that the point at which the regression line and the y-axis intersect. The y-intercept can have positive or negative values depending on what is it you're measuring. Now, make sure that you are cautious in making predictions for y based on values of x that are outside of the data range, okay? So, again, if years of education, we're not looking at 3, right? We're not looking at 3 years of education and seeing how much internet use they have. That's going to give me faulty data. That's probably going to go down, actually, and it's going to be a negative number for internet hours. That doesn't make any sense. No one can have negative hours, right? It's an absolute 0. So just be careful when you start playing with it, because mathematically, you certainly can have a predictor. Best example I have of that is somebody who, the day before their wedding, on this day, at age X, they had 0 husbands. At age whatever, they then had 1 husband. Don't start keeping going down the line. They're not becoming polygamous as we're getting older, right? Okay, so mathematically, the line would support that, but logic needs to be inserted as well. So you need to be cautious of that. Okay, I have 2 dogs attacking one another behind me. This is just semester of grace. I appreciate all of you for the grace that is having my dogs in the background. So thank you guys. Okay. So positive and negative relationships. We've already talked about a mild positive relationship, right? Where if a completely flat, straight line was a relationship that would be 0, meaning there is no relationship. If I have one that is straight up this way, this would be the perfect 1-to-1 ratio, right? This is very rare that we see such a strong relationship. This means that as one variable goes up, the other one goes up in the exact same value, okay? This one, for instance, we're looking at a slope of 0.5, so a little bit more mild of a slope. This one has a -2 slope. This is very, so again, every time one drops, it drops down 2 the other increment, okay? So you go down 2 for 1 drop on the x-axis, okay? We all remember how to do a slope line? Yeah, hopefully it's kind of in your brain still. This is a 0.33 slope, so again, that is a negative relationship, but a bit more wild. Mild, not wild, mild. Okay. Oh, no, that's good. I'm going to leave it at that. Okay, coefficients of determination. Another value for that is R². It tells us how accurate a prediction our regression model makes. So it's a test of accuracy. So if you look here, how do we measure R²? You look at your covariance for both X and Y, you square that, the variance of each X and Y, and then that is included here. That gives you R². In our example, it's 0.46. We'll talk about what it means in just a minute. The residual sum of squares, that's all of the difference between the observed and predicted. So this residual word should be a keyword. We talked about that earlier in terms of error. That's what it means. So I'm looking at all of the difference. So my line of best fit is not perfect. So that's looking at the difference between my data point and the line. And then I add up all of the differences for all the data points in my sample. So that would be your residual sums of squares. No human is completing that on a piece of paper. This is a value that will spit out at you once you run an analysis in Excel or in SPSS. Your regression sum of square, on the other hand, reflects the improvement in the prediction error resulting from using the linear prediction model. So it's your sums of square total minus your sums of square for the error. Okay. Lots of data here to talk about. Ultimately, what does it all mean? Let's go back here for just a second. This is all telling us how accurate was our line and did we reduce error as much as possible. So there are values that will spit out from our analysis that'll give us that information. That's the amount of information you guys need to know about that. Now you can test the significance of that specific variance using an ANOVA. This is what we talked about last week. So you're looking at the sums of square between, sums of square within, divided by their degrees of freedom, and you end up with your F value. Based on that F value and the F critical, you can then determine if your P value is significant, okay? This is all something we have done before. The reason why we would do that is to actually see if there is a significance in our values from it. Because at this point, doing the regression on its own does not give us a significant value. It is doing then the ANOVA within that will do it. Okay. So this is, again, a throwback of last week. You end up with your regression and your residual and your total score. From there, you have the degrees of freedom that are labeled, and then you get an F value. So we would need to first look up the critical cutoff value in the F table. Again, that's in your text that will be provided during the exam. And then you need to compare it to your actual F value. Now, let's remember from last week. Where does your F value need to lie in relation to your F critical for the analysis to be significant? Does your F value need to be greater than the critical value or smaller?
I
50-50
don't know,
shot.
but I can take a shot in the dark. It's 50-50. Greater.
Greater. 100%. Yes. So if we get an F critical, any F value that is beyond that critical value, the critical value tells us it is significant starting here. Anything more than that, it's even more significant. Okay? So if I were to look again at my degrees of freedom for F, I look at degrees of freedom 1, it's right here, down to 8, 532, which is going to be very significant. Do I have it written somewhere else? I don't, but it is. It's very significant because our other value is 175.36. So that tells me I have a significant difference between my needs. Okay, so that was all regression. Takeaway points of regression. It is when you have multiple independent variables predicting your dependent variable. It is only for interval ratio variables. It does its best job by using a line of best fit through a scatter plot to figure out what is going to be the next predicted value. So if I go up 1 for X, what is going to be my Y-intercept then? Those are the takeaways of a regression analysis. Questions about that? Any questions? No? So far, so good?
Yep.
Okay. Golly, you guys. I feel like I've got my infant here with me. Okay, so next is correlation. Correlation is something we've talked about, obviously, in the past, right? Bivariate correlation. Do we remember that? We talked about this in this class, right?
That sounds familiar, yeah.
Okay, what do we remember that it means?
Bivariant. So two variations.
Two variables.
Variables, yeah. Anyone want to help me out?
Yep.
I got nothing.
And what's the idea of correlation? What does that imply? Another word for correlation would be association, right? It speaks to the relationship. Okay, in stats, we can talk about correlation, but specifically mathematically, how are we doing that? It's through the Pearson's correlation coefficient. That is the value that we get. That's called R. In research articles, that's how it'll be labeled. It'll say R equals, and it'll range from -1 to +1, anywhere between that. So that's how you would go about and find it. Now, if it's a positive, the closest it gets to 1, the stronger the relationship. How often do we think that happens?
It achieves 1.
In the social sciences, that it gets 1, like that is the correlation.
Barely ever. I can't say never.
Yeah.
But
pretty much never. Pretty much never, because that is such a strong relationship, very unlikely to happen. The same way, very unlikely to happen that it would be -1. So either extreme, very, very unlikely in the social sciences. It's just never going to be that strong. So we're looking at a correlation coefficient that's really going to fall a little bit tighter and closer. And then we'll talk about what score it would be in order for it to be considered a strong relationship. So the Pearson correlation coefficient is the square root of my variance, and it's a measure of the association between variables. It's just the two variables. It's always going to be bivariate, reflecting the strength and the direction of the linear association between the variables. It can be positive again or negative. So again, it tells you a lot. It tells you strength, directionality, and again, speaks to the specific relationship between the two variables. It's defined as the covariance of X and Y to the product of the standard deviation of X and Y. So here it's laid out right here in the equation, the covariance of X and Y divided by the standard deviation of X and Y, okay? That gives us our correct myself up there. So R squared is right here. The correlation coefficient is just a single R, so you need to square root this value in order to get your actual coefficient. Okay? All right.
Sorry.
That was
one quick question about the
yeah.
So
let me go back.
It says square root of R squared. So is that like you square root the square root of it? So it's R squared and then you square root it, right?
So yes, I think I'm understanding your question. So yes, it is the square root of the R squared value. Yes.
Okay. Sorry, I read it and then it kind of confused me a little bit, but okay.
So another way I could describe that. Yeah, I don't have a better way to describe it than that. Your textbook talks about it. So I added this additional, I'm pointing, but you can't see where I'm pointing here. This additional formula to kind of give it a slightly more the greater understanding of it. But ultimately, you've got this R squared value, which is composed of this equation. And to get your Pearson R, all you do is you take this value and you square root the whole thing, which will give you R.
All right, perfect.
Okay. All right. So we talked about this already. So Pearson correlation coefficient ranges from 0 to 1. 0 indicates no relationship, right? They exist, but they don't have a meaningful connection with one another. An R of +1 means that the two variables have a perfectly positive association. As I mentioned before, as one increases by 1, the other increases by 1, and it's a perfectly linear relationship. Very unlikely. Inversely, if the R is -1, it indicates a perfect negative association, right? So then the line is this way. As one goes down by 1, the other goes down by 1 as well. No, as one goes down, the other one increases by 1. That's the way to do it. So the absolute value of R indicates the strength of the linear association. Tell me why it says absolute value. What are you thinking?
I guess I'm so sorry. I don't know.
Well, okay, let's take a step back. What does absolute value mean?
It's always going to be positive.
Right. So you take away, right? It's like you put the two lines around the value so that regardless whether it's a positive or negative value that goes inside the absolute value, it's going to be positive. So you take away the directionality of your line. So the reason why that looks at only the strength is whether it's -4, a -0.4 or +0.4, both equally tell you how strongly related the two are. The same one, if I said it's an R of -0.1 or +0.1, 0.1, that's the strength. It's a very limited relationship. Regardless of whether it's a negative or positive, that's really just the directionality of your line. That's all it's looking at. So if you take that away, then you just get the strength of the association. Okay. So here's more example. This is an R of 0.82. As you can see, this is the line of best fit between it. It shows a strong positive relationship. Conversely, -0.82, it's a strong negative relationship. So again, the strength, they're both very strong relationships, whether positive or negative. This is a R of 0.52. It is a moderate positive relationship, right? Because it's a little lower. And this is a -0.22 relationship, which is a weak negative relationship. Okay. This all good? Make sense? Okay. So let's talk a little bit about spurious correlation and confounding effects. So there's several, I mean, this is a huge piece about research in the research methods class that we talk about. Because when we look at setting up a research study, we need to make sure that the results we get are in fact due to the variables that you are actually collecting data on, right? That it's not due to some other confound or a spurious correlation that would be found in the data. So there's an example here. There's an article in 2004 where Michael Benson and his colleagues discussed the issue of domestic violence as it correlates to race. Now, studies and reports consistently found that the rates of domestic abuse are higher in communities with higher percentages of African-American residents. Now, does this correlation, would it indicate that race and domestic violence are causally related? Okay, causal, again, one leads to the other or one causes the other. So to suggest that African Americans are more prone to engage in domestic violence would be erroneous, if not outright racist, right? That's not a correct statement. So what Benson and his colleagues argued was that the correlation between race and domestic violence is confounded by the level of economic distress in the community. In other words, we may be measuring race and domestic violence, but there's another variable that's not being measured, which is socioeconomic status or income, which is a far greater predictor, right? That is the variable that is most highly correlated or takes up the most amount of variance for domestic violence, not race. But because race is overly represented with a lower socioeconomic group, it appears that there's a relationship. So when we look at regression models or correlational models, we always need to be very careful that what we're observing is actually accurate, that there's not another reason why that might be present. Okay, I just kind of explained all this here. Yeah, so then another way to look at it is to look at high and low economic distress in both African Americans and Caucasians, and then all of a sudden the relationship between race and domestic violence becomes less important because there's far more variance found with just economic distress. as a predictor of domestic violence. Okay, so this is where stats can lead us down the wrong path as to what is actually causing or what is most impactful of a variable, right? Okay. So we talked about regression earlier. Now we've talked about correlation. Now we're going to talk about multiple regression. It's an extension of bivariate regression, which is again 2 variables, and it extends it to more than 1 variable. So we are doing exactly the same kind of formulation, except we're multiplying each value as we go along. So you can see here as we define it, the y hat, right, or caret, it's the predicted score on the dependent variable. X1 is the score on independent variable X1, X2, the score on independent variable X2. A is your y-intercept, and then B ends up being the partial slope of each variable. So partial slope of y and X1 and partial slope of y and X2. Okay, partial slopes, I just talked about that. It reflects the amount of change in a y for a unit change in a specific independent variable while controlling or holding constant the value of the other independent variable. This is crucial. When you're doing a multiple regression, you're in a sense saying, I am controlling for this, and I think we've talked about this when we did a couple analysis 3 weeks ago. I am controlling, I'm taking out of the equation this other variable, and I'm only looking at this one. Meaning I am holding constant the other variable so that I'm only looking at the relationship between these two. Okay, so that is why it's a partial slope. Because obviously once you put them all into the equation, one is going to impact the other. So that's going to be the full slope, right? It's going to be impacted. But if I take out one of the variables, then I only have a partial slope to explain away only that one variable as it relates to the other. So another word of saying it, it's like collapsing across all other variable and just examining one variable at a time. Okay. I'll go back to describing that. This is some of the data that you would get spit out in SPSS. You guys have been robbed because you won't get to see these beautiful output scores. Honestly, if you guys get access to SPSS and you're like, I kind of wish I would know how to do this, which I just realized the ridiculousness of what I just said. But anyway, if that happens, please find me and I will gladly tutor you through the entire process and help you out. SPSS is amazing. So this is what it would look like. This is an output file for a multiple regression. What you would see is the model summary here at the top. You would see your R value, right? Correlation. R squared, kind of your variance here. You would see the regression sum of the square, the residual, your degrees of freedom, and here is your F value, okay? So if I went back to that table earlier, I would do degrees of freedom 2 from the top, I would go down 7, right? And I would get an F critical. I suspect that F critical, probably like 4, right? So this F value of 147.87, massive, right? Which is why it's super significant. It's not significant at 0.05, it's 0.000. I don't even know what the rest of the numbers are. Okay, these are my betas or my slope, okay? Here's education and here's age. My dependent variable is internet hours. So let's look at this and break it down. What does this tell us? If the relationship between education and internet hours, the slope is 0.49.
So it's closer to a positive?
Right, so if it was plugged into a correlational kind of analysis, right, there's a scatter plot, it would be more positive, you're totally right. Or for every year of education that you climb up, you go up 0.49 in terms of internet hours, right?
Yes.
Okay. So then for age, what do we think that means?
Okay, so it's negative, so it's decreasing the older you get. But so this isn't talking about education. This is just age.
This is just age. So this is the example I gave you guys to the next level. There's a little bit more data. Now we have age.
Now, so is that because we know that like with age, there's like a curve of like we increase. And so that's just the average age per year will go down 0.057 hours of internet use.
Exactly. So, but how big of a relationship is that?
Very, very little.
Very little. And how do I get further proof of that? If I go further over here, look at my significance. So it is technically significant because it's smaller than 0.05. But look at the difference here. This one is 0.000. This is very, very significant. Okay? So that's a way we would do that. So in an exam, hint, I might say to you, if you have a correlation of this, what does it tell you about the two variables and their relationship? Or here is a scatter plot. Look at the relationship between these variables. Let me now add another line in here for another relationship. Now, if we hold one constant, which is what this is doing, if I hold education constant, I don't care about your levels of education, and I just look at age, is there a relationship? Turns out not so much. Okay, so to be able to decipher that. Okay. So the standardized slope coefficient, which is right here, this beta, okay, that is a standardized value that is converted to a z-score. So that's a z-score value, so we can kind of make more sense of it. It ranges between 0 and 1, and the larger your beta, either negative or positive, identifies the independent variable with the strongest effect. So if I go back over here, this is a much stronger beta than this one. So that education has a stronger effect on internet use than does age. Okay. We don't need to talk about that because we talked about all this already. This is just terms you should have some vague awareness of. Oh, and that's it already. So things you need to know: what does it mean to have a bivariate regression versus a multiple regression? What is the line of best fit in a linear relationship between variables? What's a partial slope, and how do we minimize confounding variable? And I think there may be one more slide. But yeah. What's the Pearson R? Again, how do you calculate the slope of a line? And how do you read then a scatter plot as well? Those are the big take homes for today. I've been doing a lot of talking. So what are your thoughts? Any questions, comments?
Could I ask a general question about next week?
Yeah.
So
well, next week it's Turkey Day, so
right.
Week after that?
Yes. So basically this week we're gonna be just taking it easy, studying, and then next week or the following week after Thanksgiving will be, let me hang on.
December 2nd.
Well, yes. So we will be assigned our exam and our project, and then that will be turned in on the, oops, sorry, I'm trying to pull up my calendar. That will be due, sorry, what?
On the 4th.
Okay. Okay. Sorry, I just wanted to
You will have,
double check.
yep. So you'll see two separate documents or separate assignments. One will say exam, the other one will say special project. Once you click into exam, it's going to be a Word document. It's going to ask you questions from the chapters that we covered. This may be worth sharing again. Let's just take a peek. What is the syllabus?
I was from like chapter 7 to chapter
Yep,
yeah.
7 through 12. That's not totally accurate. 7, 8, 9, 10, 11, 12. Yeah, actually that is accurate. So we're gonna, back from October 21st, estimation, how we went about that. How did we do hypothesis testing? What's a null hypothesis, alternate hypothesis? Talking about, yeah, we did t-test before that, so we're not gonna bring that back. Bivariate tables, that's when we started touching on correlation. Test of the analysis of variance, and then regression and correlation. Yep. So
Perfect.
that exam, yep, that exam is going to cover those. It's going to be a Word document. There's going to be my cell phone number at the top if you have questions. The special project is going to have probably 3 files. One will be, well, probably just 2 files, actually, now to think about it. I'll have the instructions written out on the assignment. There's like a space, like a part for me to write on that. And then you'll have an Excel spreadsheet and a code book that will describe each of the variables in the spreadsheet, because it's not always super intuitive what each value means.
Okay.
And obviously you can reach out and answer questions, or I'll answer questions. You can ask them. Yeah. Okay, I'm gonna save this lecture and upload it to our YouTube page as well. So if you need to reflect back on today, definitely can do that. And then otherwise, I wish you guys all a very happy Thanksgiving. Stay safe out there. Hope that you all have great time with your families. And yeah, I guess as the campus dorms, they're just closed through the end of the year now.
Yep. All back home.
Crazy.
Gotta be out by Friday. They're not closed yet.
Ah,
Not yet. Oh, I'm glad to hear that. Yeah, that's super stressful. Okay. All right. Best of luck, you guys. We'll talk again soon.
Thank you.
See ya.
Happy.
Bye.